Hi, I'm Alina.
And I'm Ava. Today we are going to talk about periodic trends.
We will be focusing on the four main periodic trends, which are
atomic radius, ionization energy, electronegativity, and ionic radius.
So let's start with atomic radius. So what exactly is atomic radius? Atomic radius is the distance from the center of the nucleus to the boundary of the surrounding shells of electrons of each chemical element, or in simpler terms, the size of the atom. So, as you move down a group, atomic radius increases, but as you move up a group, atomic radius decreases. Elements in the same group exhibit the same patterns because of their number of valence electrons. On the periodic table, as we move down a group, atomic size increases because there is an increase in the number of occupied principal energy levels, or N. In group 1, the alkali metals, all of these elements have one valence electron, or one electron in their outermost shell. As you move downwards, as N increases, a shell is added, but there is still only one electron in the outermost shell. This pattern continues with the rest of the periodic table, with group 2, the alkaline earth metals, having two valence electrons in the outermost shell. As we move across the period to the right, the atomic radius decreases. This happens as protons are added to the nucleus as electrons to the same energy level or within the same shell. The electrons on the outermost shell are pulled closer to the nucleus because of its increased nuclear charge and electromagnetic attraction. The force of attraction between the nuclei and the electrons increase, causing the size of the atom to become smaller. There's a trick we can use to help us remember this. Visually, this change in size can be represented by the image of a snowman. The bottom of the snowman is the heaviest, while the top is the smallest. So as you move down the snowman, the size increases, as does atomic radius when moving down the periodic table. Going across a period relates to a knocked-over snowman on its side, in which the radius becomes smaller as you move along the side of the snowman to the top of its head. Using this, we can determine that the element with the highest atomic radius is francium, while the element with the smallest atomic radius is helium. Let's review this concept. Arrange the following elements in decreasing atomic radius: silver, cesium, sulfur, carbon, and sodium. So the order of the elements should be cesium, silver, sodium, sulfur, and carbon. Following this trend, you start with elements lower on the table, moving up left to right.
The next periodic trend we will be looking at is ionization energy. Ionization energy is the amount of energy to remove one valence electron. To remove one valence electron, it is called first ionization energy. To remove a second valence electron is called second ionization energy, and to remove a third valence electron, it is called third ionization energy, and so forth. As you move across a period from left to right, the ionization energy increases. And as you move up a group, the ionization energy increases. So, the ionization energy trends are opposite to the atomic radius trends. To go along with Alina's representation of periodic trends with snowmen, for ionization energy, you want to remember that the trends correlate to an upside-down snowman. Ionization energy increases as you go left to right across a period because it takes more energy to get rid of electrons and to gain protons. As a result, the ionization energy increases since protons increase as you go left to right. The ionization energy decreases as you move down a group because less energy is required to lose electrons, so it's easier to remove valence electrons in the outer energy level. There is the most ionization energy the closer the element is to having a complete valence shell, because there will be more resistance to take an electron away from a complete shell since the element is already stable. To review, let's do a couple examples on putting elements in order based on their ionization energies. To start, put the following elements in order of increasing first ionization energy: carbon, oxygen, fluorine, boron, beryllium, lithium, and nitrogen. First, let's mark all these on the periodic table. Now that we have all these elements located, when putting them in order of increasing first ionization energy, we will need to start with elements lower on the periodic table and work our way left to right. Since all the elements are in the same row, we just have to work left to right. Lithium is the smallest, then beryllium, then boron, carbon, nitrogen, oxygen, and fluorine. Let's try one more example, this time dealing with the second ionization energy. Which of the following has the highest second ionization energy? Sodium or magnesium? Starting at sodium and then moving to neon, the valence shell will then be complete, causing the ionization energy to be lower as a result of the stability. But when you take away one more electron to get to fluorine, the ionization energy increases because it takes more energy to move away from a stable state provided by the full electron shell. On the other hand, starting at magnesium and then removing an electron to get to sodium will not be difficult because ionization energy is lower on this side of the periodic table, due to the elements not having anywhere close to a complete valence shell. Then, when one more valence electron is removed, you are at neon, which is a complete valence shell. So, it takes less ionization energy to reach this state. Therefore, sodium will have a higher second ionization energy.
Another periodic trend we will use is electronegativity, or the tendency of an atom to attract a shared pair of electrons towards itself. This trend correlates with the trend of ionization energy, and the upside-down snowman analogy can be applied. So, as we move down the periodic table, electronegativity decreases. But as you move up a group on the periodic table, electronegativity increases. As you move across a period from left to right, electronegativity increases, but as you move across a period from right to left, electronegativity decreases. We can use our knowledge of the other trends to help explain electronegativity. We know as you move down a group, the atomic size increases because of increased distance between the outermost shell and the nucleus. The distance leads to lesser attraction of electrons towards the nucleus, as the nucleus now exerts less force on the outermost shell. Therefore, the tendency to attract a shared pair of electrons decreases, so electronegativity decreases. Electronegativity increases across a period because the number of charges on the nucleus increases, which then attracts a bonding pair of electrons stronger. As the atomic size of elements decrease across a period, the outermost shell is pulled closer to the nucleus, leading to greater attraction of the electrons towards the nucleus. Because the outermost shell is now closer to the nucleus, it can attract the shared pair of electrons more towards itself, leading to an increase in electronegativity. The most electronegative elements are the halogens, which are the most reactive and located on the rightmost side of the periodic table. These smaller atoms hold more proton than its energy level, or have a higher effective nuclear charge. This means that these elements hold electrons the best and therefore have a greater ability to attract pairs of electrons. There is an exception to the electronegativity trend, as the noble gases in group 18 do not have electronegativity because they have a full shell of electrons and do not form bonds. Let's review this concept. Determine the mistake in the arrangement of atoms from lowest to highest electronegativity: cesium, iron, germanium, silicon, and argon. The mistake is argon. Argon should be ordered first, as noble gases don't have electronegativity.
The last concept we will be covering today is ionic radius. Ionic radius is the radius of an atom's ion in ionic crystal structure and after an atom gains electrons or loses electrons. The ionic radius increases when an element goes from a neutral atom to an anion. This is as a result of anions being larger in size than the neutral atoms because adding more electrons creates repulsion. With more electrons than protons, the positive charges are not being drawn towards the nucleus, which makes the radius smaller. On the other hand, the ionic radius decreases when an element goes from a neutral atom to a cation. Cations are smaller in size because cations cause the neutral atom to lose electrons and have more protons, which draws the electrons towards the nucleus and decreases the size of the atom. Okay, now that we understand the difference between cations and anions regarding their ionic radiuses, let's do an example. Would Na to Na plus have an increase or decrease in ionic radius? It would have a decrease in ionic radius because when sodium is converted from its neutral state to cationic state, it loses an electron, causing the size of the molecule to be smaller. Therefore, its ionic radius is smaller. Let's try another example. Would N to N3 minus have an increase or decrease in ionic radius? It would have an increase in ionic radius because when nitrogen is converted from its neutral state to an anionic state, it gained 3 electrons, causing the size to increase and therefore the ionic radius.
Thank you for watching.
We hope you all learned more about periodic trends today.